Hello everyone. We have already seen Introduction to Queuing Theory. Today we shall see the self-service model of queuing theory. A self-service model is a model with Poisson arrivals, Poisson departures, infinite serving channels, general queue discipline, infinite capacity of the system, and infinite capacity of the calling source. Now, since the capacity of the calling source is infinite, we can have infinite number of customers joining in the system. Also, the capacity of the system is infinite. So, infinite number of customers can be accommodated in this system. In this model, the customer himself is the server, and since the capacity of the calling source and the system both are infinite, the number of servers will also be infinite in this case. This is a common example of online bookings and any self-service counter in any operation. It is also an example of immigration death process. In this, you will find that the mean arrival rate lambda n is equal to lambda, which is constant for all values of n, and the mean departure rate mu n is n mu, directly proportional to the number of customers, since the customer himself is the server. Let us now see the model step by step. If we assume the differential equation of birth-death process, which are given by equation 1 and 2, and try to substitute the values of lambda n and mu n that we have defined in the earlier case, this is what we get. So equation 3 and 4 are equations 1 and 2 after substituting the values of lambda n is equal to lambda and mu n is equal to n mu in equation number 1 and 2. We shall now have to use these equations, equation 3 and 4, under steady state conditions. So let us first see what are steady state conditions. So steady state conditions state that limit t tending to infinity, pnt will tend to pn, that is it will no longer depend on the value of t, and since pnt is a constant with respect to t, its derivative pn dash t with respect to t is going to be 0, and hence the limit of a constant 0 is 0. If we try to incorporate these two steady state conditions in equation 3 and 4, we get equations 5 and 6. The left hand side becomes 0 because pn dash t is 0, and on the right hand side you can see the tag bracketed t is gone from each and every value of probability. Now we shall simplify these two equations to get the probability distribution Pn of number of units in the system at any time t. If we try to solve equation number 5, we find that equation number 5 will yield us the value of P1 in terms of P0. That is, we get mu P1 equal to lambda P0, which is in turn P1 is equal to lambda by mu P0, or equivalently rho P0. Let us now substitute n is equal to 1, 2, 3 step by step in equation number 6 and see how does the value of P1, P2, P3 proceed. If I substitute n is equal to 1 in equation 6, the equation that I get here consists of three terms on the right hand side, one with P1, P0 and P2. I shall keep the term with P2 on one side, transfer the other terms on the other side, and simultaneously substitute the value of P1 in terms of P0 and lambda and mu. Hence I get 2 mu P2 equal to lambda plus mu into lambda by mu times P0 minus lambda P0. If I try to open the bracket, sorry, In the first expression of the right hand side, you will find that the second term of the bracket cancels with the second expression on the right hand side of my equation, and hence I will be left with 2 mu P2 is equal to lambda square upon mu P naught. If I take 2 mu to the right hand side, it goes to the denominator, and hence this can be simplified to P2 is equal to rho square upon 2 P naught. Let us now see what happens when we substitute n is equal to 2 in equation 6. You can see that on the right hand side we have P2, P1 and P3. Let us keep the term with P3 on one side and the remaining terms to the other side. Once that is done, we can simultaneously substitute the values of P2 and P1 in terms of lambda, mu and P naught. So this is what we get. Now if we try to open the bracket in the first expression on the right hand side, the second term of the bracket will cancel with the second expression of the right hand side, and we will be left with 3 mu P3 equal to lambda cube upon 2 mu square P naught, and that will yield us to value of P3 if I take 3 mu to the right hand side, which again goes to the denominator. Hence I have P3 equal to lambda cube upon 3 factorial mu cube P naught, which can be equivalently written as P3 equal to rho raised to 3 upon 3 factorial P naught. If we try to generalize, we can obtain the equation of Pn. So Pn can be arrived to as rho raised to n upon n factorial P naught, which is visible in the subsequent slide. So once this is done, the next step is to obtain the value of P naught. Now P naught can be obtained by taking the sum over Pn from 0 to infinity and equating it to 1. Sum of all probabilities always resulting into total 1. Let us now substitute the expression of Pn in this. P naught is independent of n and can be removed outside the bracket, that is the summation, and we have summation of n running from 0 to infinity rho raised to n upon n factorial. This summation is nothing but e raised to rho. So we get P naught into e raised to rho equal to 1. If I try to take e raised to rho to the right hand side, I get P naught equal to e raised to minus rho. On substituting this value in the expression of Pn that we have at the top of the slide, we get the general equation of number of units in the system at any time Pn is equal to e raised to minus rho, rho raised to n upon n factorial for n going from 0, 1, 2, 3 up to infinity equal to 0 otherwise. This is Poisson distribution with parameter rho. So a self-service model exhibits Poisson distribution with parameter rho. Let us now see what are the measures of the model. Now for a self-service system, it is expected that since the customer himself is the server, there will be no waiting time for the customer. The customer should be able to join the queue as soon as so customer service should start as soon as he enters the system. So here in this model, we expect that the waiting time of the customer in queue is 0. Waiting time of the customer in the system is only equal to his service time, and hence queue length will also be 0 because the customer is directly going to the serving portal as soon as the customer enters the system. There is no waiting period here. So let us see what are the values of these measures mathematically, because logically we are getting the value of queue length 0 and waiting time in the queue as 0. Also waiting time in the system should be equal to service time. Let us check mathematically whether the logic is true or not. So first measure is the expected system length, which is the expectation of n, that is summation n Pn, n running from 0 to infinity. Now this is the derivation of mean of a Poisson distribution. So the steps follow and we get the value equal to rho, the most expected value. Now let us see the remaining measures as I told you earlier. Expected waiting time in the system is calculated as Ls upon lambda by Little's formula, and Ls is nothing but rho, which we just calculated. If I substitute rho as lambda upon mu, lambda will cancel and I get 1 upon mu, which is the mean service rate. So waiting time in the system is nothing but mean service time. Waiting time in the system is nothing but mean service time. Next is the expected queue length. Expected queue length is the expression of LQ, which is given as Ls minus lambda upon mu by Little's formula. If I substitute Ls as lambda upon mu, I get 0 as expected, and if LQ is 0, WQ also has to be 0. So the mathematical models also come out to be the same as the logical models. Thank you.